All right, welcome to topic 9.4. I started making the video and it didn't work, so this is a very quick crash course of me trying to fix the video that I already made. So what you guys worked on in topic 9.3 builds into this topic of 9.4. So what we did in this topic is we mathematically figured out the heat involved in allowing the heating of a single phase and what happens during phase changes. So as our review, what I did here is I identified essentially the 5 regions of this heating curve. I know that it's heating because temperature is going up. And so if you recall, what we see is we see these sharp slants anywhere that we have a single phase, because we're heating that single phase, to the point of these plateaus where phase changes are taking place. Again, temperature remains constant during a phase change. So I've numbered this as 1, 2, 3, 4, 5, going from solid, melting, the liquid stage, to vaporization, to this gas stage or steam. These constants are the expectation is you need to know how to use them, not to memorize them. And so I'm going to explain when you use them in the math part here. So everything I've done here in step 1 is the heating of the ice. So what we first have to look at is we have 5 calculations to do to then work on getting the total amount of heat. So what happens here is we can use MCAT, the specific heat equation, to solve for heat, how much heat is involved with a specific mass of water, knowing its state and the change in temperature. Well, up here, I told you that you had 1 mole of it. Molar mass of water is 18, so we're heating up 18 grams of water in the state of ice. So what I did here is I took 18 grams times the specific heat of the solid stage right here. I found my delta T, final minus initial. So it ended at this segment at 0 degrees Celsius minus a negative 80. So it's essentially a positive 80. Multiplying it, it took 2,991 joules to allow this first step to happen. Now we can't use MCAT in step 2 because it's all in one phase. So what we're looking at is the energy involved using the enthalpy. That again, we're looking at what kind of energy is involved to allow a phase change to take place, in this case melting. Another word again for melting is fusion, so the enthalpy of fusion. The mass is never going to change. You still have 18 grams of water that's now in the solid/liquid phase as melting is occurring, and that uses 333 joules per gram. So those grams units are going to cancel and you get 5,994 joules. Now in step 3, you're looking at a single phase. So we're back to using MCAT. Because again, it's all in one phase. It all has the same specific heat. We have a change in temperature. So we still have 18 grams. Liquid water is 4.18. That might sound familiar from first semester. And the delta T is 100 minus 0. So 100 degrees Celsius to give you 7,524 joules. Now here for vaporization, we're back to a phase change. So we're going to use M times the enthalpy. And this is the heat energy or the energy involved in vaporization at boiling point. Notice the value here is much larger than the value we used with fusion. So again, vaporization is 2,260 joules per gram. So it takes significantly more energy to allow boiling to happen than what it takes for melting to happen. And that's all due to relative intermolecular forces between the molecules, in this case water, and the amount of energy distinguishing a liquid from a gas. There's just so much more energy involved to get it into the gaseous state or steam. So then your last step here is the finishing of the heating of the water to your final temp. So it's all in the steam form or gas at this point. So we have MCAT, so 18 grams times the specific heat of the vapor or steam. And then it ended at 140. So 140 minus 100, you get 40-degree temperature change. So then what I did here to get the total heat is to find Q sub T, or total Q, is all you do is add these 5 answers up. And that's how much energy it took 18 grams of water to go from minus 80 degrees Celsius up to 140 degrees Celsius. That's 58,659, which in kilojoules is 58.659. Also, these I just rounded to whole numbers. I didn't get too worried about significant figures and all of that. So like I said, just round them to whole numbers and we're just going to call it good there. Okay, so then the last thing is we found our Q to be a positive value. Q means that it's endothermic, that heat is going in, which we then measure that with, and it is reflected in a temperature increase. And that means heat has to be absorbed. So then on the reverse side, cooling curves really aren't much different in terms of the process. So we still have 5 steps. However, and you're only going to work with water, you'll see here that you are starting from 140 degrees. So we're starting with steam. So steam, liquid, solid. So your intermediates, where your phase changes happen, condensation is your step 2, and freezing/solidification is your step 4. So you work out the 5 steps. First one being the cooling of the steam using MCAT because it's still in one phase. There is a slight difference, and I goofed up when I wrote my temperatures. It's final minus initial, so it's 100 minus 40. That makes a difference because then our answer is minus 2,940 joules. You're still using the enthalpy change at your phase changes. So, and in this problem, let me mention the 36 grams came from the given problem. So make sure you look at how much water that you're starting with. So then when you look at condensation, it tells you here that the enthalpy change is a negative 2,260 joules per gram, which is where I got my negative 81,000 from. Working through the rest of it, I have my MCAT for my liquid here. And so again, 36 grams, liquid, specific heat, and then again, 0 minus 100, final from initial. Again, you keep that pattern of a negative. Freezing, you're going to use its enthalpy change of solidification. That is the negative 333 joules per gram. And again, 36 grams. Last but not least, you're looking at how much heat was involved in the remaining after the phase change of cooling the solid or cooling of the ice. And so for step 5, we're going to use MCAT. There's 36 grams of ice now. It has a specific heat of 2.07. And then again, your final temperature was 80 and the initial temperature here was 0. So minus 80 minus 0 keeps you with negative values. Again, you're going to find your total heat, you add up your 5 answers, and then you can swap it over to kilojoules. So in this case, our Q value was negative, meaning heat is leaving or released, which is an exothermic change. If you have questions on these problems, feel free to come see me.